Hey class, today we're going to start chapter 14.6 and this section is about reaction mechanisms, and we have split this into part 1 and part 2 as well. So as a little bit of an introduction, a balanced chemical equation for a chemical reaction indicates the substances at the start of a reaction, and we call those reactants, and those present at the end of the reaction, which we call products. But so far we haven't learned any information about what happens between these steps, part A to part B. So, the steps by which a reaction occurs is something called a reaction mechanism. This reaction mechanism can describe a lot of things, such as which bonds are broken, which ones are formed, if any of the atoms change their positions within the atom and is bonding to something new, etc. So, there are a couple of types of reactions that we're going to learn about. First is elementary reactions, and these are defined as reactions that occur in a single event or step. Later on, we're going to learn about multi-step reactions, which again occur in multiple steps. So let's focus on elementary reactions. One thing to note about elementary reactions is that the number of molecules that participate as reactants are going to tell me something about its molecularity. Now, what is molecularity? Well, there are three types we're going to define: unimolecular, bimolecular, and termomolecular. Uni is when you have a single molecule or reactant is involved. So again, when I say molecule, I mean like a single reactant. Bimolecular are when you have two reactants occurring, and termomolecular, like tertiary, means three reactants. However, one thing to note about a termomolecular reaction is that these are very rarely encountered as an elementary reaction or a single step reaction. Here we have this table in your notes. So it shows you uni, bi, and termomolecular, and then how they can happen. So uni is, again, a single reactant. Note that for an elementary reaction, we're going to talk about this, the rate law is going to be equal to my molecularity. Here is where we have an example of bi, so something reacting with itself, so we get A to the second order. Or we can have something reacting with another different reactant to get A to the first and then B to the first order. Termomolecular can, of course, happen three different ways. Something reacting with itself three times, where you get to the third order. Something reacting together plus something different, so A to the second, B to the first, and etc. So like I pointed out on the last slide, one thing to know is that the rate law can actually be kind of derived based on the molecularity of the elementary reaction. And this only works for an elementary reaction. And you cannot tell if something is going to be an elementary reaction just by looking at its balanced chemical equation. Experimental tests have to be done, and typically I will tell you that this is a single elementary reaction, and then you know that you are allowed to use this rule. Now, multi-step mechanisms. Many reactions have multi-step mechanisms, and multi-step mechanisms, what that means is that they consist of a sequence of elementary reactions that happen together. So, for example, if I was having the reaction NO2 plus carbon monoxide yields NO gas and carbon dioxide, this actually happens in two steps. The first part of this step or this reaction would be nitrogen dioxide reacting with itself. And here it forms nitrogen trioxide plus nitrogen monoxide. Then what happens is this nitrogen trioxide that was formed in the first part of the reaction actually then reacts with carbon monoxide to make my end product of nitrogen dioxide and carbon dioxide. Now, one thing to note is that chemical equations for an elementary reaction in a multi-step mechanism must always add to give the chemical equation of the overall process. All that means is step 1 and step 2 should add up and cancel to equal our overall reaction or overall process. So this up here is my overall reaction. Down here, step 1 and step 2. So what do I mean by that? Well, first, what you need to do is eliminate substances that appear on both sides of the equation. So what we're going to do is we're going to do that. Here I have an NO2 on my left, and over here I have my NO2 on my right. And then over here I have an NO3, and then an NO3. And again, what's left is my NO2, CO, NO, and CO2, which again are all parts of my reaction. The other part of this slide that we were just on is identifying what is an intermediate. Now, an intermediate is neither a reactant nor a product of a reaction. So it wouldn't be in the overall reaction. However, the other key part of this definition is it's formed in one reaction or one step and then consumed in the next step. So if you were looking back at our example, this one was here at the start, and this one is here at the very end. So this would not count as an intermediate. Something that would be an intermediate is right here. Notice that it was formed. So this was formed. And then over here, it was immediately consumed. So it was used up. So NO3 is actually the intermediate. Here we're going to do a couple example problems. So it says, it has been proposed that the conversion of ozone into O2 proceeds by a two-step mechanism. So here we have step 1, and down here we have step 2. First, I want to describe the molecularity of each elementary reaction in this mechanism. So for example, in step 1, if we look at this has one reactant, so this is considered unimolecular. Okay. For step 2, this has two reactants, so this is considered to be bimolecular. Now on your homework, I'm going to have you guys give the rate law of these. And remember, if you're giving the rate law of an elementary reaction, it's just going to equal whatever reactant that you have. So for example, rate here would equal K concentration of O3. And down here, your rate would equal K of O3 and then O. Next, it says write the equation for the overall reaction. So here we need to start canceling what is the same on both sides. Notice here I have oxygen, and here I have oxygen. And then we can start combining. If they're on the same side, like these O3s, I now have two O3s. And then over here, these O2s are on the same side, so 2 plus 1 gives me 3 O2s. And then it wants me to identify intermediates. Remember, this is what is formed and then immediately consumed. So this would be my oxygen and gas form. Here's another practice one. If you would like, you should pause this video and see if you guys can do it yourself. Now let's check to make sure what you got was correct. First, it says, again, describe the molecularity of each elementary reaction in this mechanism. Here, for my first one, it was a single reactant, so unimolecular. And then here for my second one, there are two reactants, so this is bimolecular. Next, it says write the equation for the overall reaction. So we're going to cancel what is the same on both sides. Here, MoCO5 is the same, MoCO5 is the same. Now, some people might actually cross out PCH3 and then PCH3, but you cannot. This is a single reactant. This, however, is one big compound. There's no positive. It actually forms a huge compound there. So that is one thing. So we can't cancel them out because they're not the same. So here we're going to rewrite the overall reaction. So let's rewrite what I have left over on my reactant side. And then we're going to write what we have left over on my product side. Then we need to identify our intermediate. And so again, here this one was formed and then it was immediately used up. So MoCO5 would be considered my intermediate. What we're going to end on is talking about rate laws. Now, we did talk about how if you were an elementary reaction, your rate law is dependent on your molecularity. And that is because it is a single step, so it's only dependent on that step. However, most reactions actually occur by mechanisms that involve two or more elementary reactions together, and each step has its own rate and its own activation energy. So that means that these steps are dependent on one another. Oftentimes, one step is a lot slower than the others, and therefore the overall rate of the reaction cannot exceed the rate of the slowest elementary step. It's kind of like traffic. If traffic is backed up or slow, it's going to dictate the speed on a highway if you're not able to get past the backed up cars. So this slow step is called the rate determining step because it's going to determine the rate of the overall reaction. Now, there are a couple ways where you're going to see this play out. I'm going to teach you when the slow step occurs first, and then on the next lesson, I'm going to teach you when it occurs second. So again, we're going to focus on the easy one today. It says mechanism with a slow initial step. So again, this is when your slow step is first. Tomorrow, we will look at when your slow step is not first. Here it says we can see the relationship between the slow step in the mechanism and the rate law for the overall reaction by considering the following example, where the first step is considered the rate determining step, and we know that because it says it's slow. One thing to note is first what we're going to do is we're going to give the overall reaction because we need to get a little bit of practice with that. So overall reaction, we need to cancel what is the same on both sides. So we did this earlier. We canceled out NO2 and we canceled out NO3, and it gave us the following. NO2 plus CO yields NO plus CO2. Remember, our intermediate is NO3. Now, the rate of the overall reaction depends on the rate of step 1 because this is my rate determining step. So because my rate law is dependent on that step, your rate law is only going to be taking into consideration that step. So my rate would equal K. And if I'm looking at step 1, I have 2 NO2, so I have an NO2. And since I have 2 of them, it's raised to the second power. Note that even though carbon monoxide is a reactant, since it is not part of that rate determining step, my carbon monoxide actually has a 0 order. It does not affect the speed of the overall reaction at all. So here the rate law for this reaction is second order for NO2, but 0 order for carbon monoxide, giving us the following rate that I put on the previous slide. Here we can have another one. So it says the decomposition of nitrous oxide, or N2O, is believed to occur by a two-step mechanism. Here it's showing me that the rate determining step is the first one by showing that it is the slow step. So it says write the equation for the overall reaction. So we're going to go ahead and cancel what is the same on both sides. So here we have oxygen, which is the same on both sides, and that seems to be it. Next, we're going to write the overall one by combining what we have left. So N2O, we have 2 of them on the same side. Here we have 2 nitrogens on the same side, plus my oxygen O2 gas. And then we're going to write the rate law for the overall reaction. Because the rate law was the first one, we can just have it be dependent on this rate law. So here we have rate equals K N2O. And note that there's only one N2O here, so I only have one in my rate law. So this is to the first order. Usually people make a mistake and they'll put it to the second order because they see this coefficient here as a 2, but remember, it's only dependent on the first step. And that is the end of today's lesson. If you have any questions, please let me know, and I hope you guys have a great day.